Hello and good Wednesday afternoon. Thanks to Chloe for catching the fact that I did not finish off my part 2 for this video, lesson number 3. So I'm doing that real quick here and I'll upload it to Google Classroom. You'll have it shortly. Okay, that's enough of me. Let's get rid of that. So you guys hopefully were playing with the PhET and you have a pretty good idea of bond polarity and what that looks like. So what we're going to do now is practice with a few more examples. So BH3, boron trihydride, and boron has an electronegativity of 2.0. So B is our center molecule. Now remember, boron is unusual. It has only 3 bonding electrons. We call it boron the moron because it's just different than all of the other elements. Hydrogen each has 1, so this is a Lewis diagram for BH3. It only has 3 orbitals and they are all full. So 1, 2, 3. As a shape and structural diagram, it looks like this. Trigonal planar, BH3. Now we throw in the dipoles, and boron, as I said, is 2.0, and hydrogen is 2.2. So hydrogen is slightly more electronegative, so all of the dipoles look like that. They're all equal and opposite. They cancel each other out. There's no sidedness. There's no left side, right side. So this would be a non-polar molecule. Okay, let's go to NH3. Nitrogen has 5 bonding electrons. Each hydrogen has 1. So there is our NH3. And if we do that as a shape diagram, that lone pair takes up space. So it's occupying this region, pushing the other 3 down. If we use our axe method, the central atom has 3 single bonds and a lone pair. AX3E1 or AX3E is a pyramidal. Okay, and a pyramid or 3-corner trigonal pyramidal looks like this. So we have one of them dropping down, one of them coming out of the page, and one of them going into the page with that lone pair sitting at the top. Okay, so there's our shape of our pyramid or trigonal pyramidal. And we put in our dipoles. Nitrogen has a higher electronegativity at 3.0. And we know hydrogens are 2.2, so the electrons get pulled towards the nitrogen. If I wanted to put the overall polarity in, I could do the net of all 3 of those vector arrows. When you add them all together, it points in this direction. So the top of the molecule is negative and the bottom is positive. And it is definitely a polar molecule. Okay, what about BH2F? So we're back to boron, the unusual molecule, BH2F. So Lewis diagram, 3 bonding orbitals, 1, 2, and there's our third one with the F. Shape diagram, trigonal planar, BH2F. Doesn't matter which spot the F goes in, as long as it's one of the 3. Okay, dipoles. So boron was 2.0, hydrogens were 2.2, and fluorine is the highest of all at 4.0. So we draw in our dipoles. Hydrogen pulls a little bit. Fluorine pulls a lot. So even though these look the same, they're all pulling in opposite directions. This is a big dipole from 2.0 to 4.0. Overall, that swings the pull of the electrons to the right side. So that's negative, and this side is a positive pull. So again, that is a polar molecule, BH2F. So changing that 1 hydrogen up here to a fluorine completely changes the properties of the molecule, turning it from nonpolar into polar. Okay, so now we have 2 different types of covalent bonds, nonpolar and polar. Covalent bonds and molecules that can be non-polar molecules or polar molecules based on the bonds and the shape. So we'll just look at those examples and then we'll talk about ionic as well. So this little scale, which is from your textbook, shows you when you have a big difference in electronegativity. So for example, as high as 3.3, and 3.3 comes from francium fluoride. Francium fluoride. Fluorine is a 4.0 and francium is the lowest at 0.7. So that would be our extreme, our difference. 3.3, and that is all ionic. So that would definitely form an ionic bond with the francium losing its electrons and the fluorine gaining them. So you would get F1 minus and FR1 plus, which would then attract together and make an ionic bond. So there is no sharing of electrons when the electronegativity is that high. So you can kind of see this switch when you have a metal and a non-metal. The electronegativity difference is high enough, so 1.8, 2.0, 2.5, 3.0, that you're getting ionic compounds where there is a transfer of electrons. And then on this end, they are sharing electrons, so it's covalent. And if they are sharing them unequally, so electronegativity differences of like 1, 1.3, 1.5, 1.7, it is more polar. And if it's a difference of 0, then it's exactly nonpolar. So here's an unusual molecule, PH3. Phosphorus has that lone pair and our 3 hydrogens, so it's trigonal pyramidal. And when you go to look up electronegativities, they're all the same. 2.2 for phosphorus and 2.2 for hydrogen. So there are no bond dipoles. The electron pair that's in here is being shared equally. So this is actually a non-polar molecule. Non-polar, and it has non-polar covalent bonds. So non-polar molecule made of non-polar covalent bonds. And if we look at something like CH3OCH3, CH3, I'm just going to sketch this one out quick. CH3OCH3. So this isn't a perfect shape diagram. It's more like a structural diagram. But this will have a bent shape from the oxygen to the 2 carbons because oxygen has those 2 lone pairs. And oxygen has a higher electronegativity. So the dipoles both point towards the oxygen, which makes this part of the molecule negative. And this side would be positive. If we drew an overall polar arrow in there, it would look like that. So this one is polar due to the difference in electronegativities, with oxygen being 3.4 and each of the neighboring carbons being a 2.6, 2.6, 2.6. So that's a difference of 0.8. So that puts us right about here on the scale. So it's not strongly polar, but we could call it slightly polar. And really for Chem 20, you just need to be able to say, is it polar or is it nonpolar? Or is it ionic because of the big difference? So NaCl, the example they give, Na is 0.9 for electronegativity, and chlorine is 3.2. So the difference there is 2.3. And students always ask, well, what's the number? What's the cutoff? Where do I say exactly it's ionic? And there is no magic number. There is no magic difference. It's simply if you have a metal and a non-metal, the difference is big enough that it's going to be ionic. Okay, one last thing for you to try at home. get your kitchen tap so that it has a very fine stream of water flowing. And then instead of a negatively charged vinyl strip, because nobody has those, if you have a balloon in your house, blow it up, rub it to your hair. So you are putting a charge on the balloon. And then bring the balloon close to the stream of water, and you should be able to bend the stream of water. Why? Because of this. These are showing you the water molecules. And because they are polar, the positive side of each molecule will be attracted to the negatively charged balloon or vinyl strip, and you can literally bend the stream of water. It's pretty cool if you can get that to work. Some fun to do at home. If you got a little brother or sister, you can have them play with it, have some fun. Okay, if you could do that same thing with oil, which you probably can't at home, oil does not bend when charged strip close by. So if oil does not bend, the question would be why? Because oil is nonpolar. It's a hydrocarbon just made up of carbons with tetrahedral hydrogens, and they all cancel each other out. Dipoles cancel, resulting in a nonpolar molecule. Okay, I think we're close to being done here. Yes, we are. Time to practice. Okay, in your study guide, page 126 for my class, page 130 for Miss Kelly's class. I think it is Miss Kelly's crew. It's titled Chemical Bonding and Polarity Worksheet. It is a very good review of everything we've practiced. If you would like to do some additional textbook work, there it is. Okay, and I think we are done. Yes, we are. Okay, stay safe, everybody. Have a great day out there. Try and get out on your front driveway, sidewalk, get a little sunshine, and look after yourselves.